Hi everyone. In this video we'll be looking at an introduction to NumPy and PyTorch. So PyTorch is the main library we'll be using in this course to implement the various approaches we'll be coming across. And so both PyTorch and NumPy are essentially Python libraries for storing and operating on data and multi-dimensional arrays. They're both quite similar to each other in terms of their features and APIs. PyTorch includes a number of features that are specifically relevant for the context of building deep learning pipelines, which that NumPy doesn't have. So in particular we have stuff like acceleration of certain operations on GPU. We have an automatic differentiation toolset which facilitates the computation of gradients. So what we'll be saying, gradient-based optimization really forms a central part of pretty much everything we'll be doing in this course. And PyTorch also just provides a number of other utilities that just make it easy to very quickly construct pipelines that achieve that implement the application we're interested in this course. So it provides utilities for defining common neural network building blocks, gives optimization utilities, data loading and batching utilities, all sorts of other handy tools to really facilitate building the systems we're interested in this course. And so the idea in this notebook is that I'll be stepping through how we do certain basic things in both NumPy and PyTorch side by side. And so the reason we're presenting them side by side is that, first of all, the APIs are quite similar. So we want to highlight where they're similar. And occasionally there are some differences, usually somewhat superficial differences, which are good to keep in mind in the event that you'll be switching between these two libraries through the course of this, your coursework perhaps. And so I should say this is by no means an exhaustive introduction or presentation about the features of both of these libraries. And you should get into the habit of really consulting documentation to find out more about these libraries. They're full of all sorts of features which we certainly couldn't go into without taking a lot of time. And as we progress through this course, we will gradually introduce you to new tools from within these libraries, especially mainly PyTorch, to achieve to implement the methods we'll be encountering in the course. But yeah, I just wanted to point out it's good to get into the habit of familiarizing yourself with the structure of the documentation of both these libraries. Both these libraries are quite mature now and well documented, and it's just good to be on top of the documentation to know where to look for, let's say, some feature that you'd like to implement. Right, so I'll be stepping through a number of notebooks throughout this introduction. So this first notebook we'll just step through bit by bit how to do certain basic things in NumPy and PyTorch. I've prepared the second notebook specifically relating to PyTorch, which will show us best practices for implementing a typical deep learning workflow, right? So what do I mean by a typical workflow? We typically want to define some model. We want to be able to fetch training data in batches and obtain model predictions on those batches. We want to use those predictions to typically compute some loss or some cost function. And finally, we want to compute a gradient of that loss function with respect to any trainable model parameters, such that we can tweak the parameters using some gradient-based optimization method to reduce the loss and repeat. So we're always iterating through this pipeline, right? When in most of the typical deep learning workflows we'll encounter in this course, with a few variations here and there. But so by stepping through this notebook, you'll get an idea of what what the best practices are for building such a pipeline, and how the PyTorch API can be used to do this in, as we'll see, very concise way. And so I should mention both of these notebooks will be made available to you in the course material, so you can try running the code and then tweaking it yourselves. And with all that said, let's get started with the first notebook. So let's look at this first block of code here. So I should say I'm running these Jupyter notebooks on Google Colab, which is handy for you to have access to if you'd like to use GPU accelerated devices. So Colab offers free access to a GPU accelerated virtual machine for you to run your notebooks on. And just to clarify how you set up Colab, once you have your Google account and you've logged into Colab, if you want to get a GPU accelerated runtime, we'll go to the runtime menu, we'll click change runtime type, and we'll set the hardware accelerator to GPU, right? And so it hasn't changed anything in my session here because I was already logged into one, but that will ensure that you're running on a GPU accelerated machine. Now let's step through what's going on in this first block of code. These first two lines, of course, we're just importing the libraries. The common convention with NumPy is to use the alias np. In the second block of code here, we're setting the random seed. So this is a good habit to get into to ensure that your work is reproducible, because a lot of the code you'll be writing does depend at some stage on some kind of random number generation, and by setting the random seed directly at the top of your modules, this will ensure that you will be able to reproduce any results you obtain after running the code. And this last block of code here is a PyTorch specific bit of code. So first we're defining a flag checking if we have a CUDA enabled device on this machine. So do we support GPU acceleration on this machine? If so, we're constructing this torch.device object by calling torch.device, and we're asking it to create a CUDA device if this flag is true, and otherwise we're going to run everything on the CPU. And as we'll be seeing primarily in the next notebook, this is quite handy to do as a way of, so if we want to run stuff on the GPU to accelerate various operations that we can run in pipeline, can run that significantly faster if we have access to a powerful GPU. And one way of indicating to PyTorch that we'd like to use the GPU is to set this device variable, and as we'll be seeing in the next notebook, we'll be using this device variable to indicate to PyTorch where we'd like to run the code. So this is some standard stuff that you might see at the top of various modules you might be writing to implement your deep learning pipelines. So moving on to some other basic features of these two libraries. How do we create arrays? I mentioned both of these arrays are based around defining, storing, and manipulating multidimensional arrays. So how do we go about creating these arrays in the first place at a low level? There are a number of ways of doing that. So you can create arrays in both libraries from lists with a very simple, similar API. So if you wanted to create in NumPy an array with these 3 integers in it, you can just pass this list of integers into the np.array function, and that will, if we print that out, it's going to give you a representation of this array of integers. We tried to do the same thing in PyTorch, so the default data structure is this torch.tensor, and we have some indication here that this has been coerced to a floating point number, and so this is because by default the torch tensor is going to be of type floating point, so it's going to be a 32-bit floating point number, right? So whatever we pass here, it's going to be cast to a 32-bit floating point number. And if we wanted to explicitly construct an integer array, we could, for instance, use the long tensor. So this is going to use a 64-bit integer as the data type for the array, right? So we call this time, we'll see that even the string notation is giving us some clear indication we're working with integers here, not floating point numbers. So aside from constructing arrays from lists, we have other sets of helper functions. If we wanted to construct an empty array, we call in NumPy the empty function, or in PyTorch torch.empty, right? Passing in either case the shape, the desired shape of the array we'd like to instantiate. So if we pass in the tuple 3, 2, we're going to get a 3x2 array here. Same with PyTorch. And it's important to note when we call torch.empty, this is just going to populate the array with anything really. It's just it's just essentially just allocating the memory, I would guess, under the hood for this array, for the array of a given shape. If, however, we wanted to fill the array with specific values, let's say zeros, there are other helper functions to do that. We've got these zeros functions, and again, same API in both cases. We're just passing in the desired shape. So this time we're getting a 2x3. And similarly, we have utility functions for defining arrays of all ones, and for sampling from common distributions. In this case, if I wanted to sample from the uniform distribution on the interval 0, 1, in NumPy I'd call this function, again passing in the desired shape, and so this is going to instantiate an array where the entries are drawn IID from uniform 0, 1, and same thing but slightly less verbose in PyTorch. We have this torch.rand helper function producing the same result, but this time a PyTorch tensor. So moving on, let's look at some basic properties of these multidimensional array data structures. So a very important one in the context of deep learning, you'll be querying this quite often, is the shape attribute of an array. So let's just print out the B that we've defined earlier in NumPy. It's clearly this 3x2 array. If we call its b.shape attribute, it's going to print a tuple indicating the shape of the array, which is clearly 3x2 here. And same thing, same API in PyTorch below here. So just notice that I'm using, throughout I'll be using this underscore notation to denote a PyTorch variable. Sorry, rather a PyTorch tensor. So we can, because I'll be presenting things side by side, this underscore will denote that unless stated otherwise, that I'm talking about a PyTorch tensor. And we see it's the same thing, right? We call it the shape. Only this time we're getting returned this torch.size object, which is it's reporting the same information though. And then inside here we check out the fact that this is a 3x2 tensor in this case. So moving on, the dtype attribute is going to indicate what type the array is of. So arrays have to be of a specific type, data type. And we recall when we defined A, this was from that list of integers, and we got it's telling us it's of type int64, and E must have been a floating point, integer of floats. It's reporting that in NumPy this is of type float64. Let's compare now to PyTorch. So if we recall, A underscore was just a torch tensor we defined from that list. And so as I mentioned before, this is by default going to be represented as a 32-bit floating point number, and a long where we explicitly request the long integer type tensor. It's indicating it's a 64-bit integer, and same thing for e underscore here, 32-bit float. And so these two things are important to keep in mind. So when you're building your deep learning pipelines, you typically you're going to be computing one thing which you're feeding into some other part of the system, and you often need to make sure that when you're writing the code, the shapes of what you're outputting match what you're expecting at the next step, right? And so you'll be, I can anticipate you'll be calling this shape attribute quite often to figure out that you have set things to the right shape. And similarly for data type, some let's say loss functions or activation, mainly loss functions, I'd say, that you might be using in PyTorch expect tensors of a certain data type, and so you may want to query that something is a certain data type and it matches up what the loss function you're asking for. As the main example that comes to mind does match up to what is expected when you're debugging your code. So yeah, just keep these two things in mind. You'll be using them for sure. Right, let's move on to indexing. So how do we, in both of these libraries, query for specific entries in the array? So we have a number of ways of doing so. So the simplest way we can query in both cases with an identical API using this. First of all, when we're indexing, we always use this square brackets notation. And the simplest way, when we pass in just some index and indices separated by commas, where the commas indicate which axis we're indexing. So let's just look at what's happening here. So B is 3 by 2. If we query for just 0, so this is essentially saying it pull out the 0th entry of the first axis. Because it's 3 by 2, that means it's going to pull out the 0th row, right? Which is this. And it's the 0th entry along that first axis. And this is precisely what's being pulled out here. And if we want it to be more granular, so if we also provided in this case a column index for this 3 by 2 array, it's going to give us the entry at 0, 0, which is this. And this is exactly what's being printed out here. And it's identical in PyTorch, right? With the addition that I've given an example of pulling out this row here too, at index 1. And that's what's printed here. So in addition, we have this slicing semantics that we can use using the difference you'll see from above is that we're using these colons here, right? And how does this work? So let's see in NumPy, even though it works identically in PyTorch. Again, we've got this B 3 by 2. When we query for B colon 2, we're getting this submatrix, this 2 by 2 submatrix. And so what this means in words is it's telling us along the first axis, give me everything up to but not including the entries at index 2. So up to but not including. So that's going to be at entries 0 and entries 1, the first two rows. And that's precisely what's being printed here. So conversely, if we went 2 colon, this is going to say give me everything from 2 onwards, from index 2 onwards, right? So index 2 onwards. That's just the last row. Precisely what's printed here. So we can also use something in between this tail and head behavior. So we did 1 colon 3. This is going to say everything from index 1 up to but not including index 3. So that's just going to be index 1 and index 2. And that's what's printed here. And over here we're showing how we can similarly use this along multiple axes to slice along different axes. So it's a bit different here. This colon is equivalent to saying just give me everything along that axis. And so if we interpret this thing in words, it's saying give me all the rows and all the columns up to but not including index 1. So all the rows and everything up to 1 is just going to be index 0. In words, this is just the first column, right? This thing. That's exactly what we got here. And similarly here, right? We're just saying everything up to but not including row 2 and up to but not including row column 2. That's going to give us this 2 by 2 submatrix here. And just as before, the semantics identical in PyTorch. So yet another way that we have of indexing in both these libraries is by using Boolean arrays. So suppose we had, we have this array A here, just 1, 2, 3, and we defined, we define this new index here. This is checking for all the entries of the array whether or not are greater or equal than 2. And if we print the result, the index, we have an array of the same shape, which is obviously false for the first entry and true otherwise. Now, what happens if we pass in this index in the square brackets when we're indexing? Well, all it's going to do is it's going to look up, pair up the corresponding entries, and it's going to return a new array here for only consisting of the entries for which the index is true, right? So here it's only true for the latter 2 entries, so we're just going to get this new smaller array. And as before, notation, semantics, and the API is identical in PyTorch. And so keep this in mind. This could be useful, let's say, if you have, I don't know, some let's say array of observations which you'd like to filter out based on some condition. Let's say that the row dimension, suppose, captured the different observations, and one way you could filter out certain observations that meet a condition, that don't meet a condition, for instance, is to construct such an index that denotes the filter you're interested in, and then querying the array like this to only return, let's say in the example I've given, rows that satisfy that condition, right? So these are all useful things you should keep in mind for how you'd go about pulling specific things that you'd like out of these arrays. So moving on, let's look at some basic mathematical operations. We have these sum methods for adding up entries in arrays. All right, so these two things are equivalent. And so here we see the first cosmetic difference between NumPy and PyTorch. So these first two functions, in both cases, they're doing the same thing, right? They're just summing up all of the entries of the array and returning a scalar value. But often we'll be interested in summing, let's say, just across some axis. So let's say we're interested in just summing across the rows. We have this 3 by 2 array here, for example. Suppose we just wanted to sum across the rows. In NumPy, what we do to do that, we pass in this additional keyword axis and set it to 0 to indicate we're interested in summing across the 0th axis, which in a 3 by 2 is going to be the rows. And the result is going to be now this 1 by 3, right? Because we've collapsed the 3 because we've summed across it. And so this value is just going to be the sum of these two, and so on, right? And equivalently, if we wanted to sum across the columns, we pass in axis equals 1 to indicate we're interested in summing across the second axis, which is going to be the columns in this case. And we're going to sum this way now, and some of those values is going to be this, and similarly for these values, right? It's going to be this. And so the API is almost identical in PyTorch. We just have this minor cosmetic, somewhat annoying difference that instead of axis in NumPy, in PyTorch we use dim. But otherwise the things they're the same, right? Moving on. element-wise operations. So what happens if we have two arrays here, A and D, they're the same size, and we try to add them? Well, it's just going to perform addition in an element-wise fashion. Same in PyTorch. And now, important thing to keep in mind, there is this emphasis on element-wise operations, right, in NumPy. So it's important to note that the multiplication operator here, even if we had, let's say, a matrix and a vector here, this does not denote matrix vector multiplication. It's element-wise multiplication, right? So just like the addition, we're passing in these two arrays to this binary operator, and we're returning their element-wise product. And same in PyTorch. And if we wanted to perform other kinds of linear algebraic operations, we would specifically have to call some other functions, right? So for dot products, we got these dot functions, same in both libraries. And for matrix multiplication, we explicitly need to indicate that we're doing matrix multiplication, either using the mathmal function or this shorthand @ symbol, which denotes matrix multiplication. Right? It's the same in both libraries. So moving on, let's discuss broadcasting. So some of you might have wondered, in the examples so far where we saw those binary operations, the arrays were all of the same size, the same shape, sorry. So, what might happen if we tried to, let's say, add two arrays that were not of the same shape? Would it work? Would it throw an error? What if it does work? In what conditions does it work? So it turns out that in certain conditions this does work, and this is because of a feature in both NumPy and PyTorch called broadcasting. And so let's quickly jump over to the NumPy documentation to take a look at broadcasting and how it works. But in a nutshell, broadcasting involves considering two arrays that are of different shapes, and we'd somehow like to, well, broadcasting, what it involves is essentially stretching or repeating one or the other, or sometimes both of the arrays, until we get some repeated arrays that are of the same shape, and then subsequently performing the element-wise operation on those stretched, if you will, arrays, right? And so there are a number of conditions that need to be satisfied for us to be able to do that. And so the conditions are as follows, right? And let's focus on this example down here to illustrate them. So we have this A array of shape 8 by 1 by 6 by 1, and B of shape 7 by 1 by 5. Now, to check whether we can broadcast here, and turns out we can, as we shall see. First thing we're going to do, we're going to write down these shapes. We're going to align things above each other, but from the right, right? So we're going to take the trailing dimensions and we're going to line them up. And next, we're going to compare the values that are above and below each other, and see whether they satisfy one of these two conditions, right? If they're either equal, or if one of them is equal to 1, and if one of these two conditions holds for all of the pairs of dimensions, then broadcasting is permissible. And so we see in this case why this is the case, right? So here we have 1 and 5, so one of them is 1, and same for these, 6 and 1, and 7 and 1. And implicitly here, you can consider this as being like a hidden implicit 1 dimension of size 1. So we have 8 and 1, which also satisfies this second condition. And so, behind the scenes, what broadcasting will do here in the case where we have, they're different, but one of them is equal to 1, is it's going to take whatever is in the array here of size 1. And it's going to stretch it, it's going to repeat it 5 times, right? Such that we can then pair off the 5 entries here with the 5 here. Same for here. So this thing here is going to be stretched 6 times, this is going to be stretched 7 times, And this whole thing here is going to be stretched 8 times. And it's going to result in 2 kind of behind the scenes arrays that are of the same shape, of shape 8 by 7 by 6 by 5, on which we're going to perform the element-wise operation to compute the result of this broadcasted operation between the arrays, right? So this is what happens when we have the case where exactly one of them is equal to 1. Of course, in the case when they're equal, we don't need any such logic of stretching and repeating, right? Because we can pair them off straight away. Like in this case, there's no need to stretch this dimension or this one, because we can pair off the values straight away. Of course, in this array here, we'd have to stretch this first dimension by 256 and this second by 256. Right, so provided we can do that, broadcasting will work. And if we scroll a bit down, let's look at a case where it won't work. So in this first case, we have 1D array size 3 and 4. This obviously will not work, it doesn't satisfy those 2 conditions. Similarly, this will not work because in this place here we have 2 and 4, right? So they're not equal and neither of them is equal to 1. And so I would encourage you to take a look at this documentation if you'd like to learn a bit more about broadcasting. And there should be similar documentation in the PyTorch documentation if you're interested. There's an additional article here, in fact, about broadcasting concepts. But yeah, returning to our code here, I've just got a few examples illustrating what I've just described, which you can step through in your own time. So yeah, we've got a 2 by 1 by 3 adding to a 3 by 3. That's going to give us 2 by 3 by 3 according to the rules we just saw. And just below here, I have another example of a case where we're going to raise an error because we cannot broadcast. So because of this incompatibility between the 3 and the 2, we're going to get an error, right? So moving on, how do we convert to and from NumPy and PyTorch? Again, very simple. We have a number of helper methods. Torch from NumPy is going to take a NumPy array and convert it to a PyTorch tensor. And every torch tensor object is going to have a NumPy method to convert to a NumPy array. Right? Very simple. And finally we come to perhaps the most, in the context of the deep learning work we're interested in, the most important feature of PyTorch, which is the autograd engine. So the autograd engine is a very flexible tool set for helping us compute gradients of various things, essentially, right? So much of what we're concerned with in deep learning involves computing gradients of various things that we're going to use in some gradient-based optimization method to optimize some objective function. And when we're constructing all sorts of flexible structures that we want to differentiate through, and the autograd function, the autograd toolset rather, in PyTorch really makes this process extremely easy. And let's just quickly look at such an example, right, of using autograd at a relatively low level, which you may not even need to use in throughout the course of this this course. But it's good to keep in mind if you ever need to implement something yourself at a somewhat lower level than you might need to in the course. And so the example we're going to consider here is some rather synthetic, contrived example, but which captures some of the general pattern of what we're working with here, where we have some tensors which let's say we can think of, let's take this W tensor for instance, 7 by 5 tensor. I'm sampling, so the rand_n here, this is used to sample from the standard normal distribution. And so think of this W as a weight matrix, the weight matrix of parameters, right, that we'd like to optimize. Now what have I added that's different than from what we've seen so far? So I passed in this requires grad equals true argument. So what this is going to do is that it's going to indicate to the PyTorch autograd engine that, in words it's saying we are interested in computing gradients with respect to this thing, this W, right? So it's like flagging up to the library that it needs to keep track of whatever information is needed as we operate on this W, right? Construct a computation graph involving W to compute gradients with respect to W. And by contrast here, I define this X variable here, which is again just sampled from a standard normal. It's just a vector of length 5, and we haven't set requires grad equals true. So the autograd is just going to not keep track of anything needed to compute gradients with respect to X. And so in the next two lines, I'm just computing some arbitrary functions of W and X, so just pre-multiplying X by W and then summing the result just to get this scalar value Z. And let's print it out just to see that the scalar value is Z. And so typically what are we interested in the work we'll be seeing? We're going to be interested in computing some scalar valued loss function, which is going to be a function of, let's say, some data and some model, or some structures with trainable parameters, and we want to compute gradients of that scalar valued loss function with respect to the parameters of our model, right? And so in this case, let's suppose Z denoted such a loss function, so there's a scalar value here, right? Suppose we were interested in computing gradients of Z with respect to W. How do we do that? Well, it's extremely simple in PyTorch. It's just this one-liner. Take the Z tensor and call it backward method. And once you call that, the autograd engine is going to step backward through the sequence of operations that produced Z, and it's going to do whatever is needed to determine what the gradients of Z with respect to W are by propagating information backwards through the through the computation graph, and using whatever information the autograd engine logged that is needed to compute the gradients, right? And the result of all this is that for any tensors in the computation graph for which we have set requires grad equals true, in this case we just have W, its grad attribute is now going to be set. It's going to be set to some tensor of the same shape as the tensor itself, and the entries are going to consist of the gradients, right? And by contrast, if we look at X dot grad is just going to be none, right? It's not set because we haven't denoted that we need X to be something that we want to compute gradients with respect to. So another somewhat silly example here that's trying to illustrate the flexibility of this autograd engine. So all this is trying to illustrate here is that again we have this W for which requires grad is true, and we're doing just some sequence of operations here. So all I'm trying to illustrate here is that in this case the process that we took to get to this scalar value Z was quite arbitrary, right? It was just like we just wrote out some arbitrary Python code here, a for loop to compute Z, and still this works perfectly fine, right? So the autograd library is really quite flexible. We can, provided all of the steps that we've used to compute our scalar value at the end, from these various components are at each step differentiable, we can build all sorts of interesting and dynamic computation graphs that, and if we want to compute gradients through them, it's very simple. Just take the final node in this graph and call it backwards method. Just as before, this worked perfectly, even though we're essentially here differentiating through a for loop. This is perfectly valid and well defined. As we see here, the W dot grad is defined after calling Z dot backwards. Alright, so this wraps up this first notebook, which is a bit of a quick run through the basic features of the libraries. Let's move on to the next notebook now, where we will look at building focusing on PyTorch, how we build just a simple pipeline to carry out just a very basic deep learning task.